So now we're going to talk about an introduction of how a computer works. So this is going to give you an overview of the sort of topics we're going to talk about in this course. It's designed to be at a high level, so don't worry too much if you don't get all the details. We'll cover all this stuff in a lot more detail later on in the course. So there are two things we're going to talk about. The first is executing programs on a computer. We're going to talk about what's inside a computer, inside the processor, how you load and execute instructions. And the second thing is binary arithmetic. We're going to talk about number representations, addition and carries, and basically the sort of background you need to get started on Lab 1. So let's go ahead and get started with executing programs on a computer. So before we go there, what's inside a computer? So if I ask you that, what are the sort of things that you would say are inside a computer? I'm sure you've got to have a list of them. If you think about what's inside it, what's inside the laptop in front of you or a desktop computer, what are the components are there? Here's my list. Processor, CPU, central processing unit, typically look like this. This is the bottom of the processor. You can see it has lots of capacitors for power regulation and lots of pins for connecting power and input-output. Memory, so here is a RAM chip. Input-output, you got to have some way to get data into and out of the computer, often keyboard and mouse, network cards, and some sort of storage. Storage is usually a spinning hard disk, but these days it's becoming more and more common to be a flash drive. How about a computer system? How are these components connected together? Well, we've got the central processor, the CPU, and it's connected to memory, and it uses memory a lot, so it's going to have a big connection there. It's also got this input-output stuff, serial ATA, PCIe, USB, Ethernet, all the protocols that we use. And then we've got these actual devices. So we've got our permanent storage, so hard disk, our user input-output, keyboard, mouse, and things like the display. And now let's take a look at how these are all connected. So as I mentioned, memory has to be accessed a lot, so there's a lot of bandwidth there. 32 gigabytes per second of bandwidth on a lot of processors these days. So that blue line there is scaled to how much bandwidth there is. Now the CPU also talks to the input-output device, but at a much, much lower rate. And these then talk to the individual devices. So hard disks are 750 megabytes per second, far, far slower than main memory. USB to a keyboard and mouse, 1.5 megabytes per second. Displays, well, they're pretty quick because you need to update all the stuff on the screen all the time, but they connect to the graphics processor, not directly the input-output, and the graphics processor then connects to the CPU through a PCIe bus, which is about 5 gigabytes per second. So here are the parts of the computer system, and you can see the relative speeds of the connections between them. This is the sort of stuff we're going to talk a lot more about when we get to the lecture on input-output, or I/O. Now let's take a look inside the processor. So the most important part of the processor is the part that does the computation, the compute part. Here's where you do actual additions, subtractions, multiplies, the actual work that goes into calculating your algorithm. In addition, processors have data registers. These are small, fast memories where you can keep small amounts of data that you're working on. In this case, we're going to look at a data register as having 2 units in it. Obviously, the data registers has to be able to talk to the compute part so that you can take that data and actually do something useful with it. In addition, there's control logic in a processor, and the control logic takes care of things like if, then, else, looping, which instructions to execute next. And the control tells the compute which operation to do. Should it do an addition, a subtraction, or multiplication? It also tells the data registers which data should be used for that computation. We also need a current instruction. So this is the instruction that tells everything what to do. And the instruction obviously talks to the control, and then the control tells the compute and the registers what to do based on the instruction. The computer also has a memory. This is big and much slower than the data registers, but we can fit a lot more stuff in here. Here's where we keep our program and our data that doesn't fit in our data registers. And obviously we need to be able to read instructions from the memory and read and write data to the memory. So this is sort of inside our processor. But we're missing something here. Can you guess what it is that we're missing here? It's a little tricky. So say we have a C program that looks like this. It says while I does not equal 2, I equals I plus 1. Well, the tricky part here is how do we do this if? We need a way to change our control whether I equals 2 or I equals 1 or 3 or 0. And so what we need is some feedback. We need a way for the compute unit here to say, hey, I equals 2, control, you need to do something different. So we need to send the result of the compute unit back to the control, and then the control needs to use this to choose the next instruction. Now we can have all sorts of interesting behavior in our programs. So here's the basic processor. We've got memory units in purple, control units in red, and compute units in blue. So let's take a look at how we program a processor, and then we'll take a look at how the processor actually runs the program. So here's our C program. It's very simple. While I is not equal to 2, I equals I plus 1. We put this in a compiler, and the compiler is going to generate assembly code. If you look at the assembly code here, it's a lot longer, has much simpler instructions. There's no while. There's just jumps and additions and subtractions. The assembly code is then loaded by the operating system into the memory, and then you can actually execute the code. Let's take a look at a few of the details of this assembly code. So here's an instruction in our C program, I equals I plus 1. Let's see what that translates into assembly language. It translates into this here, R0 equals R0 plus 1. The compiler has put the variable I from our C program into the register 0, and here it is adding to that register. Here's another thing to look at. While I does not equal 2, how do we decide if I does not equal 2? Well, here's the assembly code. We do a subtraction. We say register 1 equals register 0 minus 2, and then we jump if 0 to somewhere else. So we're checking if I equals 2 by subtracting 2 and checking if the result is 0. If the result is 0, we jump to this done instruction here, and if the result isn't 0, we keep going until we go back around to the loop. So this is our assembly program. You're going to get all the details of this in Lab 1, so right now you just want to have a general feeling for what this program is doing. So now let's take a look at what we actually do if we run this program. So when we run the program, we're going to walk through what the processor does. The first thing it's going to do is load the instruction. So it's going to take it from the memory and take the current instruction. Then it's going to figure out what operation to do. That's in the control. Then it's going to figure out what data to use by going to the data registers. Finally, it's going to do the computation. And to do that, we need the data from the data registers, and we need to take the operation from the control logic. Then it's going to figure out the next instruction, possibly using the result of the computation if it needs to do a branch, and it's just going to repeat this over and over and over again until the program's done. So we'll cover all this in a lot more detail later on. Right now you want to get a feeling for how it all fits together. So let's start walking through our instruction. So the first thing we do in our instruction is we load R0, which is the value for the variable I in our C program, from the memory. So this is stored in location 7. And so what you see here in our memory, we're going to look at the first instruction. We're going to load the instruction as our current instruction. We're going to use that to go through the control, and it tells the data registers, load the value from memory, load value 7. It's going to then send that data back and put it in the data register. So our first instruction loaded the value from memory into the data register, and now we go on to our next instruction. Our next instruction is to subtract 2 from R0, that is, take away 2 from I and see if it's equal to 0. So we're going to load this instruction. That instruction tells our control what to do. The control tells the compute, this is subtract 2, and it needs to know what data to use. So it takes R0, because this instruction is R0 minus 2, subtracts 2 from it, and then stores the result into R1. So R0 was 0, we subtracted 2, so now R1 is going to be minus 2. So now we stored that, and now we go on to our next instruction. Now we're going to check if the result of that is 0, and if it is, we're all done with our loop. So we load our instruction again, now we're on instruction 2. This is jump if 0, R1. We go through our control. Our control says, is it 0? What do we check if it's 0? Well, it's R1. We check if R1 is 0 because the instruction says jump if 0, R1. We send the result back to the control. R1 is not 0, so we're not going to do a jump here. So we go on to our next instruction, which is instruction 3, and now we're going to add 1 to R0. So we load this instruction. The control now is add 1. It takes the data from R0, adds 1 to it, and stores the new value back in R0. Now R0 is 1. Then we go on to our next instruction. Our next instruction is a jump. This says to continue the loop. So we load this instruction. It tells the control what to do. All the control needs to do is say, okay, the next instruction is to jump to instruction 1, and now we go back to instruction 1. Now we're going to subtract 2 from R0 again to see if we've got to the end of our loop. We load the instruction. We choose subtract 2. We take R0, but now R0 is 1. We subtract 2. We store it in R1, and now the result is minus 1. We go on to our next instruction. Now we check if R1 is 0. Well, we look at R1, now it's minus 1, so it's not 0, so we're not going to jump. Now we go on to the next instruction. The next instruction is to increment R0 again, So we load that instruction. We're now going to do an add. We take R0, we add 1 to it, we store it in there. Now R0 is 2. So now we're going to go on and go around the loop again. But this time, you'll notice that the value we have in here for R0 is 2. So this time we're going to be done with the loop. So we load our instruction, we look at the jump, we look at what the control says to do. The control says it's a jump, so it just jumps. We choose our next instruction, and now we go back to instruction 1. Now instruction 1 is going to subtract 2 from R0 to see if it's 2. We load the instruction, it tells compute what to do, it subtract 2. It loads R0, subtracts 2, and stores back the result. The result is now 0. Now we go on to our next instruction. Now our next instruction is jump if 0, R1. So we load the instruction, the control tells the compute what to do. The compute says, is this 0? It looks at R1, it sends back the result, and it is 0. So now we're going to jump to instruction 5 because we finished our loop. So our next instruction is now instruction 5. We load instruction 5, we go to the control, and we crash. And why do we crash? Well, because instruction 5 is invalid. We didn't have any code in here. But if we had code, now we'd be done with our code. So that's how you execute the loop. So, you're all ready for the exam now? This is basically what this class is about. Well, of course, it's going to be the details of how do you build this and how do you make all the little parts work. But what did we do? Well, we loaded the instruction, we figured out what operation to do, we figured out what data to use, we did the computation, and we used the result to figure out the next instruction. And then we just kept repeating this. We repeated it until our loop was done in this case. So what you're going to do in this course is you're going to understand the details of this. Some nasty corner cases, particularly with loops and with dependencies. And you're going to look at performance. And you're going to understand how this all comes together in a MIPS processor.